Alright, so today I'm gonna be explaining another important article about domain adaptation. But today is just domain generalization. It means that your target is unseen during training. So the title of this article is Learning to Balance Specificity and Invariance for In and Out of Domain Generalization in 2020. We introduced domain-specific masks for generalization, a model for improving both in-domain and out-of-domain generalization performance. For domain generalization, the goal is to learn from a set of source domains to produce a single model that will best generalize to an unseen target domain. As such, many prior approaches focus on learning representations which persist across all source domains, with the assumption that these domain-agnostic representations will generalize well. However, often individual domains contain characteristics which are unique and, when leveraged, can significantly aid in domain recognition performance. To produce a model which best generalizes to both seen and unseen domains, we propose learning domain-specific masks. The masks are encouraged to learn a balance of domain-invariant and domain-specific features, thus enabling a model which can benefit from the predictive power of specialized features while retaining the universal applicability of domain-invariant features. So you see that at training time, we optimize for a combination of domain-specific and domain-invariant learned representations. Partially invariant representations are indicated as color combination. For example, blue and yellow is the green. And at test time, these learned representations that capture a balance of domain specificity and invariance allow the classifier to make a better prediction for given test invariance by leveraging domain-specific features from the most similar source domains. So domain generalization involves training a model on data denoted as X sampled from P source distributions that generalize well to all Q unknown target distributions which lack training data. So we are interested in learning a parametric model M sub theta. We can decompose it into feature extractor and task network. So task network and then feature extractor is common paradigm. And then we introduce domain-specific activation masks for learning a balance between domain-specific and domain-agnostic features. On the left, our training pipeline involves incorporating domain-specific mask in the vanilla aggregate training process. And in the middle here, you see for an image belonging to a sketch, we sample a binary mask. This binary mask, we sample it from the corresponding mask parameters, which is then applied to the neurons of the task network. And finally, on the right, you see the post-feature extraction. An element-wise product of obtained binary masks is performed with the neurons of the task network layer to obtain the effective activations being passed on to the next layer. Our goal is to learn representations which capture a balance of domain-specific components and domain-invariant components. So given K neurons at some layer, we introduce parameters for each of the source distributions. During training, for instances, from domain D, we first form mask probabilities via sigmoid operation. Then the binary tasks are sampled from a Bernoulli distribution given by the mask probabilities. Upon sampling mask for individual neurons, the effective activations which are passed to the next layer are these five, which is element-wise product of obtained activation and the sample binary mask. So here is important to ensure the masks capture neurons that are specific to individual source domains. We need to encourage specificity in the mask while maximizing predictive performance. So to incentivize domain specificity, we introduce an additional soft overlap. That is a soft overlap loss that ensures masks associated with each of the source distributions overlap minimally. To quantify overlap, we compute the Jacquard similarity coefficient, also known as IOU. This is a score among pairs of source domains. For example, domain D sub I and D sub J, this is the score of that. The calculation shows the score. And we minimize the following softmax, this kind of soft overlap loss for every pair. This is just one pair. For every pair of source domain masks, we should do it. But don't forget that this is just element-wise products. And then to summarize for a set of source domain, just sum over different pairs, sum over L.